Welcome to the next unit of our MOOC on the discrete element method advanced topics. The unit is called Advanced Post-Processing and Benchmarking, and this time I would like to start with an expert interview. I have talked to Luisa Orozco from the Netherlands eScience Center why she is using DEM simulations.
Also, for experimental physicists, it would be nice to have access to DEM simulations. For example, I used to do a lot of experiments of granular materials, but I was always stuck with the fact that I couldn't access all the information inside the particles because no camera allows you to film through other particles. So in DEM, the fact that you have the contact forces and the velocities and particle per particle information allows you to have very valuable information and to calculate way more indicators that allow you to characterize better your system.
Thank you, Luisa, for your valuable thoughts on important indicators we can derive from DEM-based simulations. But what are these indicators mentioned by Luisa? What do they have to do with contact forces? This brings me to the content of the present unit. Let us see what you will learn in the upcoming hour. We will start with the so-called continuum theory, a central theory when post-processing DEM data. We will focus on the calculation of stresses and discuss an example how to do this in very detail. This will be followed by a short but important chapter on boundary conditions. To prepare you for the final topic, we will then introduce an alternative approach to solve the governing equations of a DEM simulator. This is the so-called non-smooth contact dynamics approach. This chapter is also thought to widen your knowledge regarding algorithms for calculating forces between particles. Last, we have prepared a small set of benchmark simulations using two different simulators for you. I will briefly show you the setup and discuss some key results. Also, we have summarized recent literature for you that discusses additional benchmark simulations using different simulators. Let us now progress to the first part, the continuum theory and the calculation of stresses. We start with the differentiation between global and local quantities or properties. Global refers to a single property in our simulated domain. Often, this is a scalar quantity. Examples are flow rates through a device, for example a mixer, or the flow regime in a silo. Also, we have seen in the previous unit that we often define a macroscopic friction coefficient as the ratio of a global shear force and a corresponding normal force. This somewhat naive definition is, however, often useful when developing real logical models of granular materials. More important for us are local, often called continuum or spatially resolved properties in a flow system. The most fundamental quantity in this category is the particle volume fraction and its counterpart, the voidage. How this quantity is computed is illustrated here on the right. We progress from a per particle information, shown here at the top, to a per RVE, so volume element based information. Consequently, we lose information, i.e. that of the particles. You will see that we completely forget about the particle rotation, for example, and dissolve this information in each RVE. Similarly, we can define a local particle size or even a local particle size distribution in each of these RVEs. We will not discuss this in greater detail in the present unit, but come back later to size distribution in our unit on polydispersity. The next continuum properties that we are interested in are associated with the particle speed and also the so-called granular temperature. The latter is an extremely important concept in continuum theories of granular flows. That is why we will discuss it in one of the following slides. Last, stress, fabric and deformation information is central to many continuum theories, and I will briefly show you how to calculate this important property of a granular flow. Let me briefly come back to the void edge and its counterpart, the particle volume fraction or the packing fraction. Here you see the definition of the latter, which is quite simple. Divide the total particle volume in a reference volume with the total volume of this reference volume. Phi p depends on the stress and how a granular material is packed, hence on its preparation history. Also the particle size distribution, or short PSD, matters next to the particle's roughness and shape, and also friction matters. You see, predicting the local particle volume fraction can be difficult, and this is why predictive methods like the DEM are so helpful. The counterpart to phi p is the porosity or void edge. It is simply 1 minus the particle volume fraction. Hence it quantifies the relative void space in a granular material. Note that typically the particle volume Vp includes the pores within the particles. Hence, we need to be careful with this definition. As it is written here, the porosity does not include pores within the particles. Thus, be careful when talking about porosities, since different people can refer to different things in case the particles themselves are porous. The next super important quantity is the bulk density. It is the product of the particle density and the particle volume fraction. The reason for this importance is industrial practice. The bulk density tells us how much mass we can store per cubic meter of a bulk solid. Finally, I would like to clarify on the word particle density. This is the total mass of a particle divided by the particle volume. It is hence the mass per cubic meter particle volume, and this particle volume includes the pores within the particle. Note, rho p is not identical to the solid density in case a particle is porous.